Good morning, Miss. So today we are going to discuss the headworks and preliminary treatment from pages 46 to 76. Next slide. So for the grit chambers are there to be able to remove materials referred to as grit. These include materials such as sand, eggshells, coffee ground, and etc. The purpose of removing grit is to prevent the abrasion of pumps and reduce the amount of materials found within the pipes and channels. Next slide. So for the design criteria of grit chambers, we must know information about the grit. So the specific gravity of grit is 2.65. The diameter of the grit is 0.22 millimeters. The settling velocity is 0.075 fps. The equivalent overflow rate is 48,400 GPD per square feet. The quantity of grit is one-third to 24 cubic feet per mg and must be washed before disposal to landfill or incineration. It is usually stored in plants. There are two types of plants. The small plant, it depends on the quantity and frequency of removal, while the large plants have continuous removal. Next slide. So for the square clarifiers or the detritus tank, detritus tanks or waste tanks are designed to have a horizontal velocity of 1 feet per second at maximum flow. When it is lower than 1 feet per second, the waste would accumulate. So the design criteria of this is that the Vs should be 0.075 fps at average flow. The TD or time of concentration is less than 1 minute. The overflow rate is 48,400 GPD per square feet, and VH is between 0.75 to 1.25 fps, which keeps the grit in suspension. Next slide.
So for aerated grit chambers, the aerated grit chambers uses air to remove the grit from the water. Aeration also provides pre-treatment of the waste by removing odors and inducing flocculation of the organic material, making primary clarification more effective. By providing pre-aeration, primary treatment is improved through grit removal, flocculation, odor control, and grease separation. Next slide. So, aerated grit chamber design criteria. So for the first one, we have the rate of aeration, which is 5 CFM per feet. Next, we have the width to depth ratio, which is 1 to 1 until 2.2 to 1. And third, we have the depth, which is 10 to 15 feet. And fourth, we have length to width ratio, which is 3 to 1. Next slide.
For the primary clar- clarifiers, it is to remove settable organics, grease, and oils. As for its efficiency, it is for 50% to 65% in suspended solids. Meanwhile, it is 30% to 35% for BOD or biological oxygen demand. Also, uh, these clarifiers are shaped in circular or rectangular objects. And it is similar to a sedimentation basins, although the scum removal is provided along with the sludge collection. As for the sludge quantities, the sludge quantities are measured by the following formula. The following formula includes the specific gravity of sludge, the specific gravity of dry solids, specific gravity of water, percentage of solids, and percentage of water. Also, the quantity of sludge is dependent on specific gravity, moisture percentage, and efficiency of settling. And as you can see, these quantities are shown in the formula. As for this formula, we also use the specific gravity of sludge, the sludge volume, which is measured in gals, dry weight of solids, which is measured in pounds, and specific weight of water.
For the primary treatment efficiency, the contaminants such as BODs and suspended BODs are considered would be 30 to 35% primary treatment efficiency. Suspended solids would be between 50 to 65%. And there are two forms of BOD: colloidal and soluble or insoluble. Now, the wastewater would be considered strong when BOD would contain 260 to 280 milligram per liter, uh, and would also be considered strong when the suspended solids would be between 120 to 175 milligrams per liter, and so on and so forth, with the medium being containing BODs of 145 to 155, suspended solids 80 to 110, and wastewater would be considered weak when there's only 70 to 80 milligrams per liter of BOD and 35 to 50 suspended solids milligram per liter. Next slide, please. Next slide, please. This here is an example for the use of the determination of the quantity of sludge as shown previously in the equations. So we're given an inflow of suspended solids being 200 milligram per liter, um, uh, S sub S, which is 1.4, the percentage of moisture being 95%, and the removal efficiency of suspended solids being 60%. Next slide, please. First, we want to compute for M sludge, which is the discharge with the concentration times the efficiency, which was 60%. And we would get 1,000 pounds. And then we would apply the formula earlier presented on the obtaining the amount of sludge, 1 over S, PS over 100 over SS. Um, ooh, um, in this table, it is the advantages and disadvantages of various sewage treatment plants. It is ordered from left to right, from the lowest quality to the highest quality, being waste stabilization pond systems. Stabilization pond system overall has good plant performance, except for the removal of suspended solids, and overall good economic factors, except for the land requirement. Lower quality sewage treatment systems would be considered because they require less land. Next slide, please. This here is the removal efficiency of each contaminant. We have suspended solids in the primary treatment, which is 50 to 80%. And as it goes to secondary and tertiary, it would increase. Same goes with the BOD, phosphorus, and nitrogen, and also E. coli, which is measured in log phases. Tertiary is considered the best as it removes over 90%. It has a 90% removal efficiency for most of the contaminants, except for nitrogen, which is 70%. Primary is bad at removal of phosphorus and nitrogen. Next slide, please. This is the discharge requirements for each contaminant. BOD sub 5 with no nitrification would require 25 milligrams per liter of discharge requirements, or 70% to 90% removal. COD, carbon oxygen, COD would require a lot more, 125 or 75% removal. Suspended solids require 90%. Um, and there are also sensitive areas such as would require small treatment plants or large treatment plants. Total phosphorus would require 2 milligrams per liter uh, or 1 milligram per liter. And total nitrogen would require 50 milligrams per liter or 10 milligrams per liter. Thank you for listening.